All right, good morning everyone. Welcome to yet another class. Today we will continue our journey over the networks and figure out what are the interesting parameters that we can still extract, and you can start thinking also what you could extract in your projects. I think most of you have contacted me last week to show what papers you chose, so I see that some groups have quite challenging papers. So good luck with that. I mean, don't worry. I mean, what I want to just to remind you, don't need to go through every single subsection of every paper. What I would like you to take the sort of the main ideas from each of the papers and then compare it maybe with the idea from other paper and see whether these ideas work with the same data sets or with the same assumptions, and also think in the back of your head whether you can use it for your project. And as for the projects, also I had some questions. I think you should really start, of course it's very important that you have a domain that you like, but what's very important that you will have a good data set within that domain. And then once you have the data set with that domain, we have already some tools, what we'll see in the class, and you already have in the papers that you're going to read, that you can apply more or less on any network from any domain. So you don't need to particularly find a paper that talks about your domain and about a specific tool. So you can just take some network and take a generic tool and try to use it. Okay, you had a question?
Yeah, do we need to present the algorithms they use, if there are algorithms and stuff, and like proofs and...
I don't think you should go to the proofs, but I would like more like meta level. To say, for example, what the proof show. To say the proof maybe how the convergence or the complexity or something, and then say that this algorithm is good in that and converges always. This does not always converge, but maybe is more efficient or something. And that would give you an idea what would you use in your in your project. Maybe sometimes you have to trade off. Maybe you not always converge, but when you converge, then it's much faster. Okay. So don't be scared about them. I want it to be, how to say, useful both. So this first stage, the reaction paper, is more for you to get, how to say, acquainted with the related work within the area you want to do the project. And then project proposal should be mostly, in a sense, based on a good data set you have or you found somewhere. If you don't have a good data set, it will be very hard either to extract anything, or even if you extract, it will be maybe very hard to evaluate whether whatever you extracted is good or not. If you don't have some kind of a ground truth and sort of a level play field on what you're going to compare, say, your approach or some other approach. Okay. Good. Do you have any questions on that? Then we continue with our lectures, and just to recap what we did so far. So remember, we started from the basic notations, then we looked at what kind of graphs there exist. We talked about path, connectivity, giant component, centrality measures, and that's probably a thing to have in mind, because one of the simplest things you can do with any network, just apply some centrality measures, and already you will have a very sort of good knowledge just by looking at that and extracting the most important nodes, whether it would be people or proteins or some kind of news items. So this is already the first thing to think about. Then we discussed how to compare the rankings of the centralities. We looked at one of the or two of the, say, most important descriptors of every network is clustering coefficient and degree distributions. We looked at how real networks look like, and in particular we were looking at this paper that scrutinized Microsoft Messenger network, and we saw that these guys have a very sparse networks, very skewed degree distributions, power law, high clustering coefficient, and low diameter. So these were the things we observed. And then we said, can we design some kind of graph models that could give a rise to such a behavior that we have measured? And we started with the random graph, And we say that we have two sort of instances of this model. One is G and M, where we have exactly M edges on N nodes, and another one, which is more widely used and is also known by Erdős-Rényi random graph, is GNP model, where when you get N nodes and you assign a probability P with which any possible pair of or the edge between any pair of nodes appears. And then we were looking what interesting happens with these graphs, with these Erdős-Rényi random graphs and their properties when we start increasing P. Okay, and then what we discussed, we said as if you have a big N, like if we talk about very large networks, then if we increase probability, while probability is still below 1 over n, which is very little, and the average degree is still below 1, we don't expect to see any giant component there. So there are many small components there and there, like islands in the sea, but there is no giant component. However, if the probability goes over that threshold and becomes more than 1 over n, and if probability is 1 over n, that means on average everyone has 1 degree, suddenly the probability of a giant component goes to 1. So and all other components will have the size at most log n. And again, I wanted to sort of emphasize that these are extraordinary low numbers giving us extraordinary sparse graphs. So this threshold is just that every node has on average only one friend. So that's extraordinarily little compared to, say, n, which can be, millions and billions. And another thing which is very interesting, if we force that each node to have at least 3 neighbors, so it's not exactly like Erdős-Rényi random graph where we toss a coin, a bias coin for every possible edge, and it could be that even with relatively high P's, some of the nodes might not have any neighbors, just they were unlucky. But if we force each node to have at least 3 neighbors, so every person has to connect to 3 other random persons, then we will not prove it, but I tell you this proof that asymptotically, almost surely, that means with probability that goes to 1 when n goes to infinity, the graph will be totally connected. And we will use this feature to prove something a bit later today. And so the most interesting thing about this Erdős-Rényi graphs is that the Erdős-Rényi graphs exhibit so-called threshold phenomena that for any monotone property, and monotone property is a property when you increase P, something monotonously either increase or decrease. So for example, path length should always decrease, right? Because if you increase P, you can only get more links thrown in the network, so the path length will only decrease. Or let's say the count of triangles, which is clustering coefficient. So all these monotone property do not go linearly with P, but they have some kind of a cliff edge where they just go slowly, suddenly poof, goes up or goes down the cliff. Okay. And then today we will look at how we can prove, or let's say give a sketch of a proof, we will not prove thoroughly, that the diameter of a Erdős-Rényi random graph is basically log n divided by log d, where n is the number of nodes and d is the average number of neighbors. And if d is very little, it's basically just log n. Okay. Or it's, you can say, log of dn. And so this is quite low number, and that's what we expect from real-world networks. We'll also look at what is the average degree. And maybe you can tell me immediately what's the average degree of. Now what would you expect average degree to be in Erdős-Rényi random graphs? Remember, we have a probability P.
N divided by P, or N multiplied by P?
N multiplied by P, that's and I mean, n, if you want to be very, very thorough, is P times n minus 1, but if n is big, is P over n. But in a sense, we can think it that way. What is the number of possible edges? more or less n square, right? And for every this n square, we toss a dice of with the probability p. So we expect to have p times n square edges in total, and the average would be over n, right? So that's what would be p times n, or n minus 1 if you want to be very thorough. What would be clustering coefficient? Remember, clustering coefficient we discussed, you can interpret many ways. For example, number of triangles, or the probability that any of your friends are friends themselves, right? So if your friends are friends themselves, a triangle appears. And now, what's the probability in Euler-Schroedinger graph that any of two of your friends are friends themselves? P. So the clustering coefficient is P. And then we'll see later whether it's surprising or not. And degree distribution, maybe you can guess already. I think I showed also in the, if now you create this graph, what would be the degree distribution? Could it be, sorry?
Gaussian distribution?
Yeah, or binomial. Gaussian would be probably for continuous case. So these are the things we're going to look next, and these are the things we'll have to then put against our real world networks and see where they sort of can explain real world networks or they can't. And then we'll discuss, is the Euler-Schroedinger random graph a good model to model real world networks? Or maybe we need something better. And so here is the example of how giant components appear. Let me see if I can show you. So this is a small app that we could say, let's take a lot of number of nodes, we set them up, and we start going, and we measure giant component size. So at the moment it's like 21, 26, and here you see the p increases. So now the probability, so average degree is 1, and suddenly giant component, sort of the things went up the hill very fast. And these red guys indicate giant component. So it went basically very slow in the beginning and then later jumped up. And again, this is only, now we have like on average 2 nodes, and it's almost all the nodes are connected. And remember in this Microsoft Messenger graph, we saw that the 99.9% of nodes were in the giant component. So this basically model can maybe explain the behavior of the giant component, where you have a very small graphs and you have a very well connected connected network. Okay, so let's let me just see why oops, something, sorry. Sorry about that. Why I have this guy? Okay, now it's good. Okay, now let's prove or show that the degree distribution in Euler-Schroedinger random graph is binomial. So how would we calculate the probability that a given node has a k degree? So with what probability a given node could have a degree k in a graph? So in order to calculate that, we could think like this. Let's take out of, if it is point of view of node, which is me. Now I take any subset of k nodes within the graph, and then I have to, with probability p, connect all of them. So this is p to the power of k, right? And I also have to, at the same time, not connect to the rest of the graph. So it will be times 1 minus p to the power of the remaining, right? And then that's only for one set of k, but we have many different possible k's that I could befriend with in this graph. So it's basically n chooses k, or n minus 1 chooses k, right? So the probability that I will have a k sort of degree is basically n minus 1 chooses k, so all possible k's that I could select from the population, right? And for every of this selection, I would need to create p links, so p to the power of k, and not to create the remaining links. And if you look at this, this is basically nothing else but the probability mass function of a binomial distribution. And it looks like basically a nice bell shape, right? So what would be the mean here? Where would we expect to have a mean of this distribution? It's average degree, because here, in a sense, measure the very low case have very low probability that it increases, reaches maximum at average degree, or the mean, because the mean of the binomial distribution is basically p times n minus 1. We just discussed that this is an average degree. Okay, and the variance, if you look at the statistics course, would be p times 1 minus p times n minus 1. And now, maybe it doesn't say much now, but if we start thinking what would be the ratio between the variance, or say standard deviation, which is the square root of variance, versus the mean, basically how big or fat this bump is compared to the mean, we can say calculate the standard deviation over the mean, and if you plug in these numbers, you would see that this approximately equal 1 over square root of n, which means that for large n's, it's almost 0. So as the graph goes, if we talk about Erdős-Rényi graphs that are very large, this bump will be very thin. Okay, so we can sort of say that for very large n and the fixed p, each node ends up with almost the same degree. Okay, so we can almost assume that it's constant degree. Okay, so it's binomial, but the more you go to n, the more this thing narrows down. And clustering coefficient, again, we already discussed, but we can now make it more formal. So clustering coefficient is nothing else as we measure how many instances of edges there exist among our friends. And if I have k friends, all possible pairs among my k friends is basically k times k minus 1 divided by 2. The 2 goes up. And that's my formula of the clustering coefficient. That's from the last time. So now, if edges disappear completely independently in probability p, then E would be basically all my friends that could have links times p. That's how many I would expect to have, right? The links between my friends. And if I put those together, I will just figure out that the clustering coefficient of a random graph is exactly p. And we also know that p, from the mean, is basically mean divided by n. And the consequence is that if, again, for real sort of graph sizes, or for the sizes of the real networks, where we have very large n's and rather fixed case, So k usually in real world grows very slowly with n, or maybe doesn't grow at all, because k, again, this is sort of depending on scalability of some kind of process. Say, how many friends can we maintain in our lives? It depends on the number of hours in the day. So we cannot have it, you know, millions of friends per node. So we are somehow fixed, but n can grow arbitrarily large. The population of the world can go very large. And if this happens, then basically the clustering coefficient becomes extraordinarily small. So it will be some very small fixed number divided by very large n. And then the clustering coefficient of graphs with large n's and small average degrees will be very small. So far what we discussed, that degree distribution is basically binomial, clustering coefficient is rather low, and then the path length. How can we sort of argue that the path length is also quite low in the Erdős-Rényi random graphs? So the intuition for the proof, and although I will not prove it thoroughly, but just to give you an intuition, is the following. So say we take a tree with degree d. So again, we start from us, as we are, say me is the root of the tree. I want to see how many people I can reach in 1 hop, in 2 hops, in 3 hops, and say my fan out, or the number of friends I have, is d. So if I'm here, in first step I will reach basically d friends. So now in total I have 1 plus d nodes I know in the graph, right? Now in the second step, if everyone else also has a fan out d, and if we assume that these do not collide, basically they don't have a links back, then in the second step we will be already covered 1 plus d squared nodes in the network, right? Yes?
And we're only dealing with d, the average, not taking account of the variability of the d.
Yeah, but we just showed before that for very large n, the variability is negligible.
Okay.
So that's why I was trying to show that. So if for, of course, and that's only assumption for the Erdős-Rényi random graphs. For other graphs, that might be a problem. But for now, we assume that for large n's, basically the ratio between the variability or standard deviation and the mean is so little that we can sort of safely ignore it.
Right.
Okay.
Another question.
Yes.
So the nodes on the second line over there, they have a degree of 4. The way I see it.
Yeah, okay, so you could say that everyone has degree 4, but I mean, this is again, this is only this is a problem, right?
Okay.
So this is a d plus 1, if you like. So that would not change. So we say that there is some kind of a constant d, or very small d compared to n, and now we try to argue. So this is not a formal proof, this is the intuition of the proof. Formal proofs are a bit more boring, and I mean we want to get the glimpse why. Okay. So the first why is in a sense that what I wanted to sort of tell you, that the majority, if we see that there are no collisions, and meaning that all the next wave will only cover new nodes, which is, again, you could say similarly, look, it's not true. And this not true being that some of our friends are friends themselves, but now we just also figured out in the previous slides that in order to do that you have to form triangles, but the triangles in Erdős-Rényi graph form very, very slowly or no, seldomly. Because the triangles is basically the probability p, the clustering coefficient, and for real world sort of parameters where you have a very small fan outs and degrees and very large n's, the triangles are almost negligible, and actually the collisions happen at the very last step, most of them. So what we could say is the following, that if you do such a process, at the kth step you will be like 1 plus d squared plus d cubed blah blah plus d to the power of k. So you have now covered that many nodes, and when you look at this expression, actually the dominant component is the last, right? So this will be larger than all the rest. So you could say, let's assume that we now, at the k step, we actually cover d to the power of k nodes. Again, it's a bit dirty, but this is what we could assume. And now we also assume that there were no collisions before, because the clustering coefficient was so small. So we could also assume that, this basically expression. And then what do we say? That when we reach all the nodes, that means n should be equal more or less d to the power of k, because that was our dominant component. And then the k, or if you want now to express how many steps we needed, it's something like a log of d to n. And now if d is rather small, then this is a very small number. Okay. So, and again, this is a not very thorough proof that we can also say that we can prove by using Chernoff bounds that the random graphs are, the vast majority of this bump will be between 3d and d over 3 degree, and log 3d is almost equal to log d over 3, because basically that's what you have here. So this we can neglect. And then the collisions is basically, since random graphs are, we'll talk later, that are good expanders, they have this no clustering and very low number of triangles. The collisions mostly happened in the last step. We could sort of safely now assume or have this intuition that the diameter of a random graph is actually of something of log n. Okay, where log of d, which is a pretty low number. Okay, so it's not an exact proof, but this is the glimpse why random graphs have low diameter. And if you could see now in some experiments, for example, if you increase the number of nodes in a random graph and you measure always the average shortest path, and you keep the basically average degree constant, n times p constant, then you can see that at some point when the graphs are relatively sort of large, it doesn't matter the size, the average path length is more or less the same. So you increased a lot the n, but the average shortest path did not increase much. So that's what you expect with the log n behavior. Any questions so far? So far so good? You are somehow too silent? I didn't prepare Kahoot for today, but for next time we'll Kahoot and we'll see whether you listened well. Okay, so now the question is, now we sort of digged as much as we could into the Erdős-Rényi random graphs, and the question would be, is it a good model to model real-world networks? And say, now we compare to this previous lecture Microsoft's Messenger network, which was pretty well measured by some people from Stanford, or where was that? So we can start thinking. Degree distribution, does it explain or not? No. Why? Because
More important than others.
so basically in Messenger we have this very ugly power law that we can only see if we do log-log. And random graph has a very beautiful bell shape binomial. Okay, so that's a no. Path length? Yes, no? Remember, what did they measure? They measured that you could reach any sort of node in that graph pretty quickly. Like it was some tens, or was it that in, I forgot now, 90% you can reach in 8 hops or something. So, or was it 6.6? Anyway, so the real world sort of measurement was pretty low, and GNP gives us log n, which for the same configuration would be 8.2. So again, this is like very close, because we talk about hundreds of thousands of nodes, right? So this you can say tick, that explains. Clustering coefficient?
No.
Sorry? No, because we just figured out that for large graphs, GNP gives very low clustering coefficient. It's almost non-existent. While a real-world network, and especially social network like the messenger, I mean, there are many friends who are friends themselves. So, for example, in their case was 0.11. That means 11% of, the probability that your friends will be friends are 11%, which is rather high. And this is basically average degree over n. If you calculate, is 8 to the power of minus 8, 10 to the power of minus 8, which is like impossible that your friends are friends themselves, are very, very unlikely. Okay, so that's a big no. And then largest connected component, they measured this 99%, and it actually also explains very well with the random graphs and we can even start seeing it when the average degree is more than 1, and if you have 14, that is more than enough. So basically out of these 4 main parameters, we could explain only 2. So we could now sort of agree that this is a not good model to explain real-world networks. So we need something more than that. So then the next one I would like to cover is so-called preferential attachment model. And that model, it's unfortunate that's how life works. And we will now see which parameter it can explain. So the life works the following. Basically, the first comers usually have a better opportunities. So if you are the first comer to system, it's good for you. If you're a late comer, sorry about that. So how does it reflect to the networks? So we start with 2 connected nodes, and now we will keep on building a graph by inviting new nodes to come. And now we will say that a new node can create one link to one of the existing nodes, but we will not say that it will create a link completely at random. We will make some rule. Maybe you want to guess which rule we're going to get?
The value of the node?
Yeah, so since it's preferential attachment, it's already revealed something. We will attach a newcomer will attach to such a node which has a better value. Now what could this value be? Degree. It could be degree. That's a very good guess, and that's exactly how it is. So what we say that a new node will create a link between V and one of the existing nodes with probability proportional to the degree of that node. So in a sense, what happens is that a new node comes, it sees who is in the network, it looks at their degrees, and then the more degree a node has, the more likely I'm going to connect to it. So that's a rich get richer phenomenon in a sense. And if we do it that way, after some steps, you could see that your graph will follow a very beautiful power law degree distribution. Okay. So if you only allow to come with one edge, what will be the clustering coefficient of that graph?
Only one?
So if the rule is the following, like here, we add the node V, and this V can only connect with one edge to the rest of the graph.
The star.
Not necessarily a star, but close to that. Star would be if every newcomer connects to exactly the same node. But we don't say we connect to exactly the same node, we say with probability proportional to the degree. So say what happens if we have the first 2 nodes are there, and that node comes, at the moment, if we use that link, that rule, the probability to attach to either of them is what? Is equal, because they're both equal so far. So we will attach randomly, say to this guy. Now the 4th node that comes, now it has 3 choices, but this one has two links, while this has one. So basically, this would be like 0.5. This would be 0.25 probability to connect. And it could be it will connect to that. I mean, this half of the chance, but another half will be either of those. So maybe it will connect here, and then it's not star anymore. And then the fifth node now will have another choice. These two will be equal. This will be less equal. I mean, they're also equal, but they're less probable. And then the process continues. So it's not necessarily a star, but it's some kind of a tree. Right? And well, we always connect it. So it's all, I mean, in this case, we don't allow disconnected nodes. But the triangles cannot appear here. So to sort of try to make triangles appear, we could say, say we start with, and this is called a variation of this, is called the Barabashi-Albert model. We say we start with a connected network of some M0 nodes. We say we take 5 nodes and we fully connect them. Okay, and then we say that every node comes with now not one link, but with several links, which is say less than what we started. So we say with 3, and again connects with the same principle. So every link would connect with the principle. That means it looks at the current network, see what is the degree of the distribution, and connects proportional to the degree distribution. Okay, so in this case, the triangles could appear, but the triangles also, they would not be, I think there is not really even a formal proof for that. I'm not sure, but I think the clustering coefficient grows something like inversely proportional to the network degree, like n to the minus 0.8 or something. So anyway, so it doesn't really explain well the clustering, but explains very nicely the degree distribution, this model. And again, we can try to see how it looks in real life. If we click on the example. So what do we have here? We say we set up 2 nodes now, and we go once. So now, of course, as we discussed, this node had to connect to some other node. Now the 4th node comes and now connected not to the middle node, but now made a line. Okay, that could happen. And the next one now created a hobby. Like now there is one guy with 3. If you go further, okay, this guy didn't win, but now the 4th time it won. And if you keep on going, you could see that those guys who were the first will keep on having the higher degree. And here is the degree distribution. Okay, so you see that most of them have a degree small, like 1, but there are some guys who already have, what is this, maybe degree 8 and degree 13. So if you keep on going, you see how the network sort of keeps on growing. Can you see well, or it's not good? So you can very clearly see the appearance of the hubs. So these the rich guys, and basically most of the nodes are pretty poor, but there always are these extreme events as we discussed. So there is this heavy tail of bastards who managed to take most of the wealth, and this really captures very well the behavior of the real world networks. And that basically only gives us a glimpse in how, since what we discussed just before the lecture, that real world networks very often exhibit this power law. And the reason why is that fundamentally some processes that happen underneath to create the network. So why a link appeared between me and you in the graph, it's usually because of some kind of this rich get richer phenomena. So in a sense, this is the, how to say, again, if you're going a bit to philosophy, is a bit sad that the natural processes favor inequality. So if you, in order to have an equal system, you have to restart it with some, from a clean slate. And once the clean slate happens, when people start, making some networks, the networks usually do not behave, like Erdős-Rényi random behavior. You usually create links with biases. Biases creates rich-get-richer phenomena. You get hubs appearing, and then you get inequalities, whatever inequality means. Okay, so that's a philosophical detour, but that's how life works. And probably in all of your networks that you're going to look at, most likely you will have, you will notice that there are some hubs, there are some, rich, nodes in whatever way, and that could be partially explained with the rich gets richer processes that create the links. All right, so let's continue now. Why I always have this? Okay, so now the last thing I wanted to sort of, before the break, to tell is the following. Sometimes I would like to generate a random graph given the degree distribution. Okay? Maybe you come to me and you say, look, I measured this network. It has n nodes. It has, average maybe degree 20, but the degree distribution is such and such, and there are 55 hubs with one is with 1,000 friends, another is 500, and so on. So you might want to see how a network or a graph would look like if you would create a random edges with a given degree distribution. And that's what is called configuration model. So what we say is the following. We start with nodes with spokes. So in a sense, you come to me and say, I have a network of n, and I know a degree of each and every node. So in a sense, I know the spokes. In your real network, they are connected somehow, maybe because, again, of this preferential attachment, and friends will probably be friends themselves, will be maybe many triangles. But here, let's compare it to some kind of a null model, a reference model, where we could then say how a network would look like had we pushed the random process. So what we would say is the following. In a sense, what we could do is the following. We say, for every spoke, we make a mini node. So let's say this node A would have 3 mini nodes, node B would have 4 mini nodes, and then randomly pair them up. So have a random network on them. And then whatever happens afterwards, so say if we had a link between B and D, then we make a link in this resulting random graph with this degree sequence. And it could happen that some of the A and B now got 2 connections, and then we just say, okay, well, we will have to deal with that, and we merge it into one. So it's not a perfect sort of representation. The final network might not have exactly the same sequence that you had, but for very large n's, this will be very unlikely, so it will be more or less a good representation. And then this network could serve you as a baseline for whatever you are measuring. So if you had your social graph, if you know what is the degree distribution, basically degree of every node and how many nodes you have, you can now create a configuration model graph, a random graph with the same degree sequence or very similar, and then start comparing, say, calculate clustering coefficient or average path length, and so on. Okay, so that's another tool in your toolbox to look at. And I just want to sort of tell that this configuration model is, you cannot go with any arbitrary degree sequence, because if you come and say, I want to create a graph where you have 3 nodes, one node should have a degree 10, two other 1. It's not possible, because if you have say the graph of 3 nodes and you say that one node should have a degree 10, it might not be legal, or not be valid. So this, you have to take care that not all the degrees sequences are realizable, but for your, if you come not for the arbitrary degree sequence but from a real graph, you already know that this could happen, and then you can see what is a null model or the baseline that you can compare against. So I think I can stop now for a break, and then hopefully next models will be even better explaining our real world networks. Yes?
I'm still looking for one person for my group, so if anyone is interested.
Okay, so one thing I want to tell you, do you see every group in the canvas, or it's only, I don't know what I see, whether it's the same view as you do? Can you see all the groups in canvas or not?
Yeah.
And you see that some of the groups, what I checked just before, have still only one member. So I would suggest that you, again, organically, maybe contact these people who are, with only one member, and then suggest to join. That would be a very nice thing to self-organize.
I think the problem is that even if you see a person on Canvas, there's, as I understand you, there's no way to get their KTH email, and there's no way to contact them. Is there?
No.
Oh yeah, you agree here, yeah. So like, even if you see that there's a person, you don't know how to contact them. Like,
Okay.
Either the messaging system right on Canvas,
Right.
or you look up their email by searching for their name.
You can do that.
Okay, yeah.
If you, for example, if you add your KTH email to your Google Mail on your phone, if you then go to your contacts and search for the name that's in the KTH directory, it's busy.
Oh yeah.